In this chapter, we're going to take a closer look at hash functions and blocks as well as blockchains. How exactly do these three components that make up a blockchain or are parts of the blockchain, amongst others, work by themselves, and then how are they put together? This is going to be a hands-on session, and you are also welcome to use the blockchain demo yourself, play with it, and see whether you understand the functionalities of them. So to start off, we're going to deal with hash functions. And as we know, for Bitcoin, we are using the SHA-256 hash function. The 256 in this context stands for the fixed length of the hash that we can see down here, meaning that no matter what is typed in or what isn't typed in, you see there's a clear field here right now, and we still have a fixed length of 256 in our hash function. If I change that, for example, by typing in a dot, you see it changes, and the fixed length, however, stays exactly the same. If we now type in something like R cents P $3, so we pretend this is a ledger where we store information, and we have another transaction where S cents T $4, then we see that the hash has changed. Again, fixed length stays the same. And what's important to note here is that even if we changed the smallest thing about this, for example, added a point right here, the hash would change completely. And not only does it change completely, it also changes in a way that we cannot determine the pattern behind the change. So there's no formula that will tell me what happens if I add a letter, what happens if I add a dot, what happens if I add 10 letters. There's no pattern, meaning that if you have the hash, you cannot possibly determine what data input we put into this. However, what we can do is take out our data and put it back in, and we will see that the hash will not have changed. Thus, it is deterministic in the sense that we always get the same hash function, no matter the data input, meaning if we put in the same data input, we will always receive the same hash. Once we change the slightest thing about it, the hash will change completely in a way where we cannot go back and say this is the data that we put in. This is what makes it so secure. Now let's move on to blocks. Let's give it a bit more context. Here you can see that we have block numbers, and blocks make up a blockchain, as you know, meaning that there's going to be an infinite amount of numbers if we wanted to of blocks. However, the reason why this is turning red right now is because we have not mined the first block. And of course, you cannot mine the second block before you have mined the first one. It needs to be in order. So let's move on to the so-called nonce here. The nonce is a number used once in computational context. This is a frequently used concept right here. And what the nonces we'll get to in just a second. Then we already know the data input. We're going to use our transaction data that we already used for a hash function right here. And what we want to do now is have a hash that is valid in order to mine the block. And if we wanted to mine the block, so basically set our transaction into stone and actually execute them as well, because thus far these transactions are not executed. They are basically just listed in the memory pool. So they're waiting to be transacted, but they have not been transacted just yet, only if we have mined the block and the block was verified will these transactions have gone through. So what do we need to do to validate this block? To validate this block, we're going to need a so-called nonce. A nonce can be figured out manually by typing in random numbers, which we can try and do. But the clue is that, again, just like the hash, we cannot basically say by adding a 5 or a 3 after we've already typed in 3 sevens, for example, we'll change the hash in a way that will deliver the desired outcome. Now, what is the desired outcome? The desired outcome for the hash function, which is the prerequisite for us to mine the block, is to have 4 leading zeros right here. So the first 4 numbers need to be zeros in order for us to be able to mine the block. Now there's, of course, then different calibrations of all the numbers and letters that come after those 4, but that's exactly what we're looking for. But we're just looking for one of those possible calibrations. So basically the first one that we can find either manually or with the help of computational power will be sufficient. We'll be able to mine our block accordingly. Now I said that we could do this manually, so let's try this. We want to get 4 leading zeros. We've got 3 leading A's right now. That's not what we need. And I could basically sit here all day. You see here, I have 1 leading 0, but it takes a while to even get to 2 leading zeros. So as you understand, it is quite hard to manually mine a block. But if we let a computer mine it for us, it will run through all the possibilities that we've just tried to find manually by typing in random numbers into the nonce. It will do it for us. So right now we have found a hash with 4 leading zeros, and the corresponding nonce is 11,295. With this mining, now our transactions are included in the block. Now let's move on to the blockchain. And what you will see here is that we need to type in our data, of course, first, that we want to validate and transact. And we will press mine again, and we will receive the hash that we already know. And what you will see here in the previous block, this is German for previous, is that there's just zeros as a hash. Now, why is that? Because we are using block number 1 right now, so the first one in the chain. So obviously there is no previous block that we could take the hash from. Now the hash for this block obviously is this one right here. And what we can see in the second block is that the previous block hash is listed right here as well. So let's mine this one as well, because we do not have 4 leading zeros just yet. Now that this one is validated, let's also validate the third one. We can also mine the 4th and the 5th one at the same time. And now let's go back and see what happens if we try and change anything in the previous block. So for example, messing with the nonce will turn all other blocks following in the blockchain invalid. Why is that? Because our hash down here has changed, and thus our previous hash in the following block has also changed, and it's not matching up anymore with what the block used to say. So we basically need to mine it again. Now we see that the rest of the blockchain is valid again because the nonce has been re-established. Now, if we changed anything about the data, what would happen then? Say our transactions took place here, we would see the same thing. Our hash would change in a way that makes the following blocks invalid as well. So that doesn't work. And as you can see, the longer the chain, the more ingrained the hashes from the previous blocks become in the blockchain. Because if you have block 4 and 5 following block 3, you basically have the hash of the previous block written and as part of the data set from the previous blocks in the next blocks as well. So blockchain is, so to speak, a very intertangled way of storing and transacting data. Now, if you want to learn more and find out for yourself whether you understand this concept, head over to Blockchain Demo and try it yourself.